our normal. So I am really excited to introduce Dr. Roxana Daneshjou, Derm Twitter royalty today. So Dr. Roxana Daneshjou received her undergraduate degree at Rice University in bioengineering. She subsequently completed her MD PhD at Stanford, where she worked in the lab of Dr. Russ Altman. During this time, she was a Howard Hughes Medical Institute medical scholar and a Paul and Daisy Soros Fellowship for New Americans Fellow. She's completed dermatology residency at Stanford in the research track, and now she practices dermatology as a clinical scholar in Stanford's Department of Dermatology, and also conducts artificial intelligence research with Dr. James Zhu in biomedical data science. Her research interests are in developing diverse data sets and fair algorithms for applications in dermatology, artificial intelligence, and we are thrilled to have her here with us today. So over to you, Dr. Daneshjou. I think you're muted.
Sorry. So I'm just going to share my screen. I hope everyone is doing well today. I am sort of an informal speaker, though I find that people generally don't interrupt to ask questions. But what I wanted to say is that if you have a burning question on a particular slide, you should feel free to ask it. It's probably a little bit hard to do with the chat, or if our great moderators want to keep track of the chat, I'm okay with questions being asked in the middle. I find that generally people don't do it, but I don't have a problem with it. But I'll go ahead and start, and I'll also be happy to take questions at the end. I will be talking about artificial intelligence in dermatology with a particular focus towards fair and equitable AI, which has been a major focus of my research. So this is where some people think we are. And you've probably been bombarded by these headlines. And I get a lot of questions from dermatologists who have a little bit of anxiety about AI in dermatology. So these kinds of headlines where it's like, man against machine, AI is better than dermatologists at diagnosing skin cancer. Google claiming that its AI is as accurate as dermatologists. Headlines that say like, the AI doctor will see you now. Plenty of people in the tech world saying, oh, we're, doctors and dermatologists and pathologists and radiologists will be obsolete in a couple years. It's interesting because many of those statements were made a couple years ago and clearly have not come anywhere close to fruition. This is where we actually are when it comes to dermatology. So most dermatology algorithms don't have transparent data. They don't report diversity of data sets. And the data used to build algorithms detecting skin disease is too white. It's focused really on white skin. And so today, what I'd like to do is just go over some fundamentals. So how do you define artificial intelligence, machine learning, and deep learning? What a neural network is, how are AI models in dermatology developed, and sources of bias in AI models for dermatology, and then potential benefits and applications that could be coming down the line. My goal really in giving these talks and to talking to dermatologists across the country is to help you gain an understanding of what's going on in the field of AI, and hopefully try to equip you to ask the important questions whenever you read a paper. The same way that dermatologists, you may not run a clinical trial yourself, but when you read a clinical trial, you know what questions you need to ask about the patient population and what kind of biases might exist in the trial. My hope is that by the end of this talk, you will have some grasp about what the important questions are that you need to think about whenever you read an AI headline or an AI research study. So some definitions, especially because these terms are used interchangeably, and even I myself will sometimes use them interchangeably. It's just quite common. But artificial intelligence is the large umbrella term for any technique that enables computers to mimic human behavior. And machine learning is a subset of AI techniques which use statistical methods to enable machines to improve with experiences, so with example data essentially. And then deep learning is a subset of ML, which uses multi-layer neural networks in order to train and create these models. And for the most part, we will be focusing on deep learning because deep learning has been used particularly for image-based tasks. And in dermatology, we're obviously a very visual field, meaning that we have a lot of image-based tasks. So what is supervised learning? Supervised learning it falls under the umbrella of everything I described before. It just means that it's using techniques where you give example or training data for the machine to learn. So labeled training data. It's not that the algorithm is just looking at the data and making sense of it by itself. It's given many examples of like what it's, what each thing is, and is able to learn from that. And so the example I like to use is the one of my daughter, though she's actually older now. This photo is just as the pandemic was starting, and thinking about ways that she likes to learn. And so, as she was growing up, we started to try to teach her about what different animals are. And so the way that she learned is that every time that we saw a dog, we would point this out to her and say, this is a dog. And in her brain, she would develop some kind of representation of what a dog is, and what things are dogs and what things are not dogs, and how to separate these things from one another. And so she might see this animal and say, oh, look, it's furry, it has 4 legs, has a cute face. This must be a dog as well. And we would say, no, this is a cat, it's not a dog. And so in her mind, she would make some adjustments to what was a dog and what was now a cat. And so she might see this animal and also call it a dog. And we say, no, that's a little lamb. And so once again, she would make some kind of adjustments from there, until finally, when she sees this labeled example, she says, okay, is this a dog? And we say yes. And now whenever she sees a dog, she has a pretty good accuracy at identifying which things are dogs, which things are cats, and which things are not dogs. And so this task of her learning to identify dogs, it was not done in isolation, right? Like at that point in her life, she had gone through the world and looked at objects and noticed that there are lines and there are textures and there are colors. And so she didn't just come into this task without having some sort of like background. And actually in machine learning, we do a similar thing. We have this data set called ImageNet, which has millions of labeled images of different objects. And many of the neural networks we use are actually first, before they ever try to do some other kind of task, they're pre-trained on that data set. And so that data set is very useful because, like my daughter going through the world, it helps these neural networks be able to identify things like edges and shapes. And we're going to dive in just a little bit more into how these neural networks work. And so if you hark back to high school biology, you will recall that there were these fundamental experiments performed by Hubel and Weissel looking at visual perception with a cat that was looking at a vertical line of light that was rotated. And what they found is that in the primary visual cortex, there were particular neurons that were activated by the movement of this light. In deep learning, we're not working with real neurons, obviously. We're working with what we call artificial neurons, but what they are these sort of mathematical constructs that learn from example images. And so what happens is, let's say your task is facial recognition. You would put you would have the training set, as I mentioned, this is all supervised learning. You would have a training set of images of faces with identifiers that go along with faces, and you would train the network on that to be able to make a correct prediction. And in this network, there are different layers of these neurons that perform mathematical functions, and then together they output, what they think the result should be. And what we've found is that the behavior that appears to happen is that earlier layers of the network pick up on more basic features such as lines and edges, similarly to the primary visual cortex that was picking up lines. But as we go deeper in these layers, they actually begin to combine these features and can recognize things like eyes or noses and lips. And then finally, there's a combination of those features to be able to begin to recognize a particular face. And so with skin lesions, it's a similar thing, right? Like it begins to, and as I mentioned before, many of these networks are first pre-trained on large data sets such as ImageNet. So they have some basic understanding of shape and texture and lines. And so then when they look at a skin lesion, they may start to pick up first on, angles in the lesion, colors in the lesion, textures in the lesion, and put that together to basically output what the diagnosis might be. And so when we're thinking of this at a high level of how these models get built, this is a common framework for deep learning models within medicine, though it doesn't always have to be this way. Usually what you get is you pick a regimen for designing this, and you have a data set, usually retrospectively collected. And so that's probably what you see in dermatology is a lot of like papers where it's been written on some data set collected in a clinic, a large data set, and they'll train the model on that data set, but then they'll leave out a portion of that data and call that their test set. And so that data is supposed to never be seen by the algorithm, and it's supposed to be a way to test whether or not the training has worked. Now, unfortunately, that's usually where most things end, and most of the headlines that you see are simply models that have been built that way, using retrospective data that's been split into a training set and a test set. But really, if you want to take the pipeline all the way to its end, and where people claim that we are, which we're not, and that's clinical deployment, you need to take this model. You can't just rely on retrospective data, and you need to start doing some pilot testing and prospectively look at how well the algorithm performs in its intended use setting. So if it's intended to be used by clinicians in clinic, then that is, that's sort of the mode that you want it to be used in. And really, at that point, you should, when you do your pilot study, you can assess whether the model impact is as you expected, or if it's doesn't perform as well as your original study on retrospective data. Now, a lot of work that has been done in this space, including papers written by myself, we feel that in order for things to really move forward into clinic, it can't just be pilot studies, particularly for things that could be algorithms that are trying to make diagnosis. You really need a randomized controlled trial to demonstrate that the algorithm works significantly better than what we're doing at baseline, and that there are no adverse events with the use of that algorithm. Now, one of the problems is this whole pipeline is very reliant on data. And so if you give it biased data, you will get a biased algorithm out. And so I hope you kind of recall from the prior slides that I showed that like these algorithms, there's nothing magical about them. they're really learning from the data examples that they're given. And so opportunities for bias exist at every stage of algorithmic development. So, for example, problem selection. We have a paper that's currently under review looking at the kinds of tasks AI algorithms are selected to do in dermatology. And we find that the focus on the kinds of tasks that they do actually are leave out, patients with skin of color. So, for example, tasks around pigmentary disorders are far less often seen than tasks around detecting skin cancer. And then data collection is another major area. And actually, that's going to be the focus of most of my talk today. But I just wanted to be clear that the data is not the only issue. We have to be very cognizant when we're reviewing this research to look at every stage of the pipeline. So outcome definition. So, these algorithms are using retrospective data. And so there might be biases that already exist in the healthcare system that are being encoded into the algorithms. And so that's one thing that we have to be careful about. During the development process, there are opportunities for bias, and then also in the post-deployment. So how the algorithms are monitored and audited after the fact. All right, so we're gonna hone in on the data because I think all of these things are important, but it's a topic that would take quite a bit of time to review. So talking about inequity or equity in dermatology AI algorithms, people started to ring the alarm early. Dr. Ade Adamson wrote this excellent perspective piece in JAMA Dermatology before a lot of research papers came out supporting this fact, basically opining about the concern that algorithms were going to be trained on data that was not representative of diverse patient populations, and that in turn, the biases in these algorithms would actually make existing health disparities worse instead of better. And then, of course, more data sort of news articles came out as tech companies got into the algorithm game, and it turned out that, Dr. Adamson was sort of predicting what the future was going to be in terms of dermatology AI algorithms. What's the issue? So part of the problem is dermatology at baseline. And I know this is global derm talk, so a lot of what I'm saying is maybe a little bit US centric, and I apologize for that because I know that across the world, people see diverse patient populations. But in the US, we have issues with our textbooks and representation within dermatology. And so, for example, Dr. Jules Lipoff has this paper where he sort of assessed the common dermatology textbooks used particularly in the US for training dermatology doctors, and found a significant underrepresentation of patients with brown and black skin. Dr. Jenna Lester has this amazing TED Talk that I encourage everybody to watch on why skin disease is often misdiagnosed in dark skin tones. And she had also published during the COVID-19 pandemic, showing us how this was happening in real time, that as people were publishing the cutaneous findings of COVID-19, there was essentially a lack of representation of these same findings in dark skin tones. And it's not, the issue, representation is a huge issue, but there are many layers to it. So for example, photography in skin of color, again, a US centric sort of comment, but in the US, we are not necessarily the best trained to take good photographs across diverse skin tones. And actually, historically, the way that photography has been put together is quite biased. So, for example, up until a couple decades ago, there were, for color balancing, when you take the photo, you have to sort of balance the colors up against a standard. And the color balancing was based on a model that was white, and these were called Shirley cards. And so digital cameras may still have differences in color balancing that can affect skin tones, and this is not well quantified. If you go to YouTube, you will see videos of people taking photos of their skin with different types of cell phones and posting it and essentially showing how their skin tone looks very different between phones. And so because of this, there is this like discordance between what color looks like in real life and the color captured by images. And so you can, as you can imagine, if the photography is not as good for a particular skin tone, this can lead to bias in the algorithm's performance. And Dr. Jenna Lester and others, including myself, actually put together this sort of best practices for photography in skin of color. Essentially, one of the important things is to use natural light, and because the flash artifact will often obscure like the lesion or not help you be able to assess it. And so we also have this image where we looked at different lighting effects on photography. So this first image is actually the natural light, and this last image is highlighting hair. So for hair images, B and C are actually with flash photography. And so you can see actually his mask is blue, and his shirt is blue. And so you can see how the color is affected by the flash in the flash photography compared to what the ground truth is here. So photography is a potential source of bias. And then another thing that people have done is sort of try to assess bias in these algorithms by labeling skin tones when they're assessing the AI algorithm. How well does it perform across different skin tones? That's some of the research that we've done, which I'll touch on later. But the Fitzpatrick skin type is often used, but it has limitations, particularly for dark skin tones. Now, some of you may say, but Fitzpatrick wasn't actually designed to assign color. That is correct. Fitzpatrick was originally designed to look at how easily you burn or tan in order to make assessments about chemophototherapy and phototherapy. But what's often happened now in practice is that people make an assessment of Fitzpatrick by looking at skin color, eye color, hair color. And particularly in AI research, people have been using this scale in that way, which I know is not the intended use. But part of the issue is that a scale of 6 skin tones probably doesn't adequately, doesn't adequately capture the diversity of human skin. And the other point to make is actually when the scale was first designed, dark skin tones were left out entirely. They were added on later, so it was almost like an afterthought. And so when we're thinking about how we assess skin tone, we need to think thoughtfully about how to have better scales that can help us quantify the biases that might exist in our data sets and in our algorithms. Now, I'll say this with the caveat that everything else I talk about in this talk actually uses the Fitzpatrick skin tone scale. And part of the reason is, again, I think we need a better alternative, particularly for assessing AI. However, even with this scale that's only, is 6 different buckets, we can pick up on quite a bit of inequity and bias in the algorithms. And so currently the state of things is such that even with the 6-point scale, we can see a lot of evidence of biases. And so one of the things that we did is, reflecting upon everything that we've just talked about, we wanted to look at sources of bias in AI dermatology data sets. And so we did this scoping review assessing 70 research papers published in the domain of AI or deep learning in dermatology. And our findings were several things. One, that AI data sets in dermatology are siloed. What that means is that they're not shared. This probably doesn't surprise very many people, but just to give you an idea, in this diagram, every purple square represents a research paper, and every circle that represents a data set. The circles that are in red means that the data set is inaccessible to us. We cannot see what kind of images are included in it. We can't explore the data set. And every circle that is in green represents a data set that is free and publicly available for use. And number one, as you can see, has generated a significant amount of research. And this is the International Skin Imaging Collaborations, or ISICs data set, which this is kind of shows how open data sets promote open science as well. And so because we didn't have access to the data sets, we had to make do with looking at the research papers and seeing what they report out about their algorithms. And what we found is that a larger portion than expected of the 56 papers that looked only at skin malignancies or skin cancers, everything in dark blue represents papers where they did not use biopsy diagnosis as the label for their images. So what does that mean? And actually, this is the case for many of the top famous papers in AI and dermatology. It means that they labeled an image as melanoma without having the biopsy confirmed diagnosis. So how did they label those images? Well, what they did is they took those images and they showed it to 3 dermatologists, and they asked them, do you think, what do you label this skin disease as? And they used that as the label for training the algorithm. Well, why is that a problem? Well, studies have shown that basically you need to, an average dermatologist may biopsy 7 to 8 suspected melanomas before diagnosing one. And so the hit rate is not the best. And what that also means is that if the image is a melanoma, but it's a melanoma that is a surprising melanoma, the labelers likely mislabeled it. And so these algorithms are learning off of data that may be noisy and not biopsy confirmed. The other thing that we noted is that these data sets in dermatology are likely not representative. As I mentioned, we didn't have access to most of the data sets, so we could not look and see, how diverse that data looked. However, when we looked through the research papers, we found that the majority of them did not describe at all what skin tones were included in the data set. And in fact, the number for skin tones was only 10% of the papers give any kind of description. And I can tell you that the 10% of papers that did describe that found that basically some of them excluded dark skin tones completely, or they underrepresented those groups. And so while we don't know what 90% of the data looks like, we can do some extrapolation from what we know from the data that was described, which is a little bit concerning. And this was sort of the impetus behind the creation of the diverse dermatologies data set. It is an adjudicated biopsy-proven data set across multiple diseases and skin tones. It has 656 images, and we tried to balance across all the skin tones, but we also matched Fitzpatrick skin types 1 and 2 and 5 and 6 so that we could do direct comparisons of those 2 groups and test algorithms out. And so what we did is that we took 3 algorithms that had previously been touted to perform really well. So Model Derm, which actually has a newer version. So we actually worked with the older version of Model Derm because the newer version was not out yet. But the older version was trained with 220,000 images. It's predominantly white and Asian patients. And then the performance, so 0.91 is like perfect performance, meaning that it's able to delineate between a benign and malignant lesions perfectly. So 0.93 is pretty good. We did deep derm, which was trained on mostly white patients, included Stanford data, and it had a AUC of 0.88. So really, these are good numbers. And HAM 10,000, which was trained on an ISIC data set. So these are algorithms that have really good performance on their original data. And in fact, some of these algorithms spurred the headlines that we read originally about how good these algorithms are and how they might replace dermatologists one day. So let's see what happens when we apply these algorithms to our new data set. So the first thing that we notice is that, so this purple dot are the dermatologists. We had 3 dermatologists also participate in this. And I will say that this data set is very hard. When I was reviewing it, I was sort of surprised because they're all biopsy proven images from an academic medical center. So every data set has biases, and the biases of our data set is that it's difficult. It's from an academic medical center. It's not meant to be representative of everything out in the real world, but it's just another public data set that people can use to benchmark their data. And so all the algorithms have significant drops in performance on our new data set. This is not unexpected because we know AI algorithms are quite sensitive to shifts in data, things like lighting or even location. If there's something different about the kinds of diseases that are seen in that location, these algorithms are quite sensitive to these kinds of what we call distribution shifts in the data. But the really interesting thing was that they did far better on Fitzpatrick skin type 1-2 than Fitzpatrick skin type 5-6. And so the closer you are to this red line, the worse your performance. And so they had a significantly worse performance, and we did some statistical tests and showed that there was a significant difference in sensitivity for picking up a skin malignancy between light and dark skin tones. And so, as I had mentioned before, almost all those, pretty much all 3 of those algorithms were trained on data that came from light skin tones. So the question is, how can we close this gap in performance? And one thing we can do is that we can do something called fine tuning, which is we can take these models and we can train them on additional data, additional diverse data, and help them learn how to identify skin diseases across all skin tones by doing this. And so what we found is that, and we didn't have access to Model Derm's code. We had only access to code for 2 models. We found when we do this, we not only boost general performance, which is not surprising because it's learning some of the differences between the data sets, but the important thing is that the gap that existed between Fitzpatrick 1 and 2 and 5 and 6 in performance can be closed once you train on a data set that includes diverse skin tones. And so our message here is this kind of demonstrates the importance of having data sets, diverse data sets that are used for training these algorithms. Because if we don't, then we end up with algorithms that perform differently across our patient populations. And when we do, then we can actually fix these problems and develop algorithms that perform equitably across different skin tones. And so I know that was a lot of everything that can go wrong in terms of AI in dermatology. And so I do want to talk about some applications and some things that are exciting and potential for the future. So 3 different short stories, because I am cognizant of our time. improving telemedicine photos, human in the loop decision support, and bias detection. So when the COVID-19 pandemic hit, telemedicine was already hot. However, here at Stanford, we basically everything became telemedicine overnight. And one thing we learned very quickly is that even though we are in the age of Instagram and Facebook and people love to take selfies, they're not very good at taking photos of their skin lesions that are good enough for us to make a clinical determination. And so this is not a real patient photo, but this is sort of mimicking some of the kinds of photos that we were getting. And at least at Stanford, what was happening is that the residents were asked to review all the photos prior to the visit and call the patients up and help them to take better photos. And so we had this idea of true image, which is, what if we made it as easy as what if we made taking photos of skin lesions as easy as when you deposit checks online using your mobile phone? And so what we did is we collected 1,700 images from visits, from telederm visits, and then asked clinicians to label the images based on whether or not they're able to make a clinical judgment on the photo. So A and B it's using this Likert-like scale. A and B are like photos that are pretty usable versus C on, these photos are not as usable. And then using this data set, we developed a model that used both deep learning and classical learning algorithms and put these together to create a classifier that could say whether an image was good or bad. And then if an image was bad, give some explanation of why the image was bad. And so looking at our retrospective data sets, these are curves that look at the balance of essentially sensitivity versus 1 minus the specificity. So they look at the balance of how well the algorithm is able to distinguish between good, whatever binary classification is. So between good and bad images, between blurry and non-blurry images, between good and bad lighting. And so on the x-axis, you can also think of it as the fraction of poor quality images kept versus the fraction of good quality images kept. And so you can draw this line on the operating point. So you can say that I want to only keep, I want to get rid of 80% of the bad quality images. I want this algorithm to be able to get rid of 80% of bad quality images. And if you do that, in general, you'll be able to keep close to 80% of the good quality images as well. So that's like pretty good. Like you're distinguishing the bad quality images and you're not throwing out too many of the good quality images. And one thing, as I mentioned, we cared a lot about equitable performance. And so we looked across different groups such as skin tone, age, and gender to make sure that we weren't having huge statistically significant drop-offs in performance. And so you can see that there is a slight drop-off in performance with older patients, but it's not a statistically significant drop-off. And we continually work to make the algorithm better. And it's important for us to know how this performance looks across different groups so that we can continually push for a more fair performing algorithm. Now that's great. Like I showed you how it worked on retrospective data, but as you know, retrospective data is not how things work in the real world. And so what we did then is actually we conducted a pilot test to see how we can test true image in the real world. And what we did is we developed this web application that is secure, that can be pulled up on a patient's phone. The UI was not the prettiest UI because we wanted to just see if we could get this thing to work. If we give patients real-time feedback on what's wrong with their photos, can they use this algorithm to then take better photos for us? And so this was sort of our process. And it was very simplistic. We didn't give people advice on how to take better photos yet. That's like the next phase. We just essentially told them why, like your photo's too blurry. So then they knew sort of that next time when they take a photo to pay more attention to making sure that it's not too blurry. And so we wanted to assess whether the image quality improves with the use of True Image, and we completed the study at Stanford clinics with 98 patients. So patients who were there, we handed them a phone, we walked out, the doctor walks out of the room, is asking them to essentially mimic what they would do at home. And so of course, that's another potential thing. It's not at home, it's not in the home setting, it's in the clinic setting, but we're trying to make it as close as possible while we have the patient there and letting them take the photos of whatever lesions of concern that they have. And what we found is with the A and B images, sorry about that. There wasn't much change in the quality because the algorithm would tell them this is a good image. However, for the images that were unusable, the C and D images, there was improvement, a statistically significant amount of improvement. And the points kind of push it towards, so like if you take a C and you add 0.7 to it, it comes closer to a B. If you take a D and you add 1.75, it actually also becomes closer to a B. And what does that mean? This means that, so this is an image that is a D image, and this is an image that's a B image. And so you can see the difference in sort of the quality. You can't really, it's like very blurry here. You can't see what's going on. And here you can more clearly see that these are benign moles. And this example is not not a patient image. It's sort of an illustrative example of what that looks like. But we had a lot of patient images that the initial image actually looked like this. It was very unusable and blurry. So that's using AI for improving the patient experience and the clinician experience by taking more clear photos. Another area has been AI decision support for non-specialists. And actually recently in the Journal of Investigative Dermatology, the first prospective randomized clinical trial in dermatology was published, which was very exciting because other specialties have had several trials and this was our first one. And it was looking at how AI assistance to dermatology residents and non-dermatology trainees, whether or not that helped their diagnostic accuracy. And a couple interesting points. The algorithm used in this study was is the newest version of Model Derm. And Model Derm has had many publications, and in those publications on retrospective data, it has always beat dermatologists. Now, when we move to the real world, where there are images of diseases that Model Derm wasn't even trained on, we find that actually that performance drops, similar to what we saw when we took those algorithms and tested it on our new data set, that their performance drops. And I think this just illustrates why it's so important to do these trials and to test on external data sets and to do the prospective studies. And so in this study, they found that AI assistance, it was a small study, so they only had 4 people in each group. AI assistance did not improve the dermatology resident diagnostic accuracy. However, AI assistance significantly improved the non-dermatology trainee in diagnosing lesions. And so this is sort of an exciting finding, because it doesn't mean that, this stuff, that this decision support is useless. It's just that we have to find the settings in which it's actually creating improvements. And so as of now, the algorithm isn't creating improvements with dermatology trainees, but for people not trained in dermatology, and we know that there are issues with access to dermatological care, it is actually boosting their diagnostic accuracy. So I think this is like a pretty exciting finding and shows that how AI could be used to augment our healthcare system. And then my last story is short, and it's work that's ongoing with IBM, where we're working. So I had mentioned earlier in my talk that people have gone through and quantified biases within dermatology textbooks, particularly the ones often used in the United States. Now, the ways that those studies were done is that they had medical students essentially turn every page and count how many images of light skin tone, how many images of dark skin tone. And so, as you can imagine, that task takes hundreds of hours and is not really a feasible way of doing things if you want to be monitoring bias in real time. And so what we did in collaboration with IBM is we built this pipeline where you can essentially take the PDFs of the textbooks and do structured content extraction. So you pull out the images and figures. Then we have an algorithm that's trained to identify which things are figures or pathology pictures, non-skin images, and then just pull out only the skin images. And then we have an algorithm that essentially takes the skin images and identifies, what is background, what is skin, and tries to identify what is unhealthy skin, though that part is a little bit harder task. But once it identifies the areas of skin, it can then assess the skin tone, and then it outputs a graph of the skin tone representation. So the thing that took many, many, many hours of medical student time can hopefully now be done in a much shorter time period in an automatic way. And so we looked at 4 textbooks, and we found that our findings were pretty close to what had been previously reported. So here's ground truth, and here's what the algorithm found. So the algorithm was pretty close to what has been previously reported in terms of skin tone diversity in textbooks. So in conclusion, I think AI algorithms are going to be becoming part of medicine. I should note that many non-dermatology AI devices are approved by the FDA. It's really important for us as dermatologists to sort of be vigilant and vocal about any concerns around biases or inequity that we see in algorithm. And it's really important for us to all work towards fair and equitable algorithms with rigorous evaluation and testing. However, I want to end on a positive note with those 3 stories where I essentially showed some really interesting ways that AI could be useful. And I want to acknowledge that research is never done in a vacuum. I'm very grateful to my mentors, my collaborators, my friends, and I'm certain that not everybody that I may have left someone out, because there's just so many amazing people that I work with. But I'm happy to take any questions now.
Thank you so much. That was so insightful. And I feel like I've learned a lot. Like, just going back 10 years, I just think back to my first ever smartphone, which was the Motorola flip phone. And that could have never taken photos like this or done anything like this. So, I mean, I think, technology and healthcare is progressing so much. So we'll open the chat to questions. And I think we've already got one from Dr. Jillian Richmond about the binary in how do we overcome the binary in AI, specifically in dermatology, when we're thinking, for example, of overlapping skin conditions.
I think I would say that this is why I feel like there are not many cases where I feel like humans are not going to have to be involved in the decision making. This is why I like the idea of decision support tools or augmented intelligence, because essentially you have an algorithm that could be helping you think about, what diseases you should be thinking about, but is not necessarily making the final decision. And I will say that many times, you can set these algorithms to output like the top 3 diagnoses. So it doesn't always have to be one output, but those outputs may be wrong. And exactly, like if you have a disease that, we all treat diseases where it's like, okay, we've done multiple biopsies. We're not 100% sure if this is on the, is on the, like, it's on a spectrum of disease. We're not really like I think of MF, for example, where it's like you suspect MF, but you keep doing biopsies and there's no pathological evidence of MF yet. And then eventually the patient might present themselves. And so for that, like, how do you label that example when you give it to the algorithm? Like, humans have a better construct of uncertainty than machines, though that can kind of be programmed, but it's the way that these algorithms are designed right now. Like, the examples are labeled definitively. And so I think that the answer there is that at the end of the day, like, particularly for these kinds of decisions where there are not really straightforward answers, like, humans have to be the final decision makers.
So just to build on that just a little bit, so are we saying that in AI and specifically in dermatology right now, the place where we are is kind of, this is maybe cancer versus not cancer, instead of going down into like an AI tool being able to say, actually, this is a melanoma, or this is a pigmented SEPK, or this is a viral wart. So is it more binary then at the moment?
No. So that's just the way that so the study that I presented that we did, where we were looking at skin tone, we did look at benign versus malignant. And that was just a result of having a data set that did not have enough examples of each kind of disease for the testing. And so we wanted to get an overarching picture. But a lot of these algorithms, like Model Derm that I mentioned, actually give out disease outputs as so they say, like, the differential that the algorithm gives out is melanoma, BCC, SEPK. Like, it will actually give diseases. And that's why the people have trained these on hundreds of thousands of images. But the problem is that dermatology is huge. And so not every disease is encapsulated. And that's one thing that was noted in the prospective trial for Model Derm. They didn't control what diseases the algorithm was tested on. They wanted to make it as realistic as possible. And so there were diseases that came in through the door in their prospective study that the algorithm had never trained on, even though it had trained on hundreds of thousands of images. And what happens when the algorithm sees that? It doesn't know what it doesn't know. So it tries to fit that disease into one of the boxes categories that it's been trained on. And so 100% of the time it's wrong, right? And one thing they found that is a little bit concerning, and something that you have to think about as well, is that when the algorithm was wrong 100% of the time because it had never seen the disease, it actually pushed the humans in the wrong direction. So it actually affected human decision making. Now, there is this other fantastic paper by Peter Shandell, which is not in a trial, but it's more in a structured setting, looking at how AI human decision making happens. And this is an area of research that we need more work in. And they found that if you have more experience, you're less likely to be swayed to the wrong decision, right? You're a more experienced dermatologist, so you kind of trust yourself over the machine. And there's like a lot of ongoing research that I think needs to happen in this particular aspect of AI and dermatology, which is how humans and machines work together. When the human trusts the machine, when the human overrides the machine. Most importantly, if the algorithm is performing well at the beginning and starts performing poorly later, does the human pick up on that? And there have been some early studies in that, as I've mentioned, but I think we really need to understand how it works better.
Totally. Thank you. We've got another question from Monisha Madhumita. They say, great talk. Thank you. So fascinating. Could you please comment on the role of AI in risk prediction of dermatological conditions?
Yeah, so I think that there are a lot of people thinking about this, essentially developing risk scores or algorithms to identify patients that might develop skin cancer or disease. I think it's like very much in the early stages. Like, people have published papers on it, mostly again on retrospective data. I haven't seen anything that has gotten close to sort of actual clinical implementation, but hopefully what will happen is we'll do some rigorous studies and only take sort of the cream of the crop risk predictions that perform fairly across groups. I just actually kind of want to make a comment on what Dr. Richmond said, just because I saw it in the chat about requesting data sets. So with these, the response that you will get is that, oh, these are patient images and therefore we cannot share them with you. So that's one. And then I will say that a very famous tech company that published in a journal, a glamour journal, which is known for requiring code and data to be shared, if you email them, which we did, to ask for, even not even saying we want the algorithm, we were just like, we just want an API, we just want like not the algorithm itself, but be able to like stick in images and get outputs so that we can test it. The answer is no. So the data and even code sharing in this space is quite terrible.
Thank you. That's, I mean, that's such a shame, because obviously that would be so helpful for future research. But we've got another question from Ahmed Khalil, and they say, wonderful presentation at work. Can we in the future create algorithms that combine clinical and dermoscopy as well as conofocal and or dermatopathology?
Absolutely. I mean, this is something that we're interested in. It's a multimodal. You can input multiple images when training these algorithms. The issue is the data sets. So there are dermoscopy images, data sets. International Skin Imaging Collaboration is essentially almost all dermoscopy images, but the problem is they're not paired yet. So the issue with trying to develop these and test them is really a data problem. There's not publicly paired data. There might be some privately paired data that's not shared, but this is something that is quite feasible. But right now it's more of a data, getting the right data to train.
Okay. Do we have any more? I actually have one more kind of comment / question until others post in the chat. I thought it was so interesting how you showed that photo of your colleague with the blue mask, and how you developed that kind of SOP for how to take photographs in skin of color, and showed how the color really changes. And that brought to mind, I don't know if anyone remembers the blue and gold dress versus the
yes,
white and gold versus like the blue and black dress. And I was thinking, obviously, I mean, that's a dress, it's not skin, but like, how would the AI, how would it interpret that? Because that was something that was so subjective. I mean, I don't even know if my question makes sense, but yeah, that just came to mind.
So, I mean, it's less subjective because it's picking up on, it's like it uses RGB values from the actual pixels, right? So it's there are all sorts of color tricks, right, that human eyes can play on how the mind interprets, but the algorithms are just looking at sort of like pixel color values. But the reason I bring that up is because it's showing that two images of the exact same thing could have different pixel color values, right? And so that does affect the algorithm, right? That's why we say like lighting, actually changes in lighting can actually affect performance of AI algorithms, because it's actually using the pixel values. And so it would note that the pixel values of the blue are more towards the blue spectrum, and white, the ones that looked white, were more towards the white spectrum. And so to make it like relevant to dermatology, like essentially like erythema, how well it would pick up on erythema would have to do with how well that erythema was actually captured in the photography. And that's why flash artifact is such a huge issue. So flash artifact is like, those images when you look and it's on you, it's usually more picked up on dark skin tones, and you see white, the white of the flash reflected back. And so that white flash artifact may obscure the skin disease, and so it would affect sort of the pixel color values. So that's sort of the corollary there.
Totally. And like, we're so bad at picking up erythema in darker skin tones anyway, which obviously leads to less equitable care. So yes, thank you so much. We've got another question from Anjali Ansi. I hope I've pronounced that correctly. They say, so I have been working on image classification open source data, such as the HAM dataset or the DermNet dataset. I would like to deploy it to a real-time web app. What aspects would I need to look into?
Yeah, I mean, I guess my first question would be, why do you want to deploy it to a real-time web app? Like what for research like I'm just trying to understand why, because there have been people who have been trying to release things directly to patients, but for the most part, the performance in the real world is not good enough for our patients to be using things, even algorithms that have been tested, on a lot of retrospective data and perform well. And so, when we created our web app for TrueImage, it wasn't a public web app. It was sort of like a personal web app for testing. So I guess that's like, I guess my first question is sort of trying to understand the reason for doing that deployment.
Just in the interest of time, I would suggest that maybe Anjali tweet Dr. Daneshjou, because
yeah,
I think we've got one more question from Dr. Damsky, and then we should probably wrap up because I'm conscious of time.
Yeah, thank you so much. And we'll get you out of here in a second. But really, that was just a wonderful talk. Thank you so much. And thank you for your focus on diversity in particular. It's greatly appreciated. I'm curious if you could just in 1 minute comment on like how peer review is going for this, because I imagine, I think you sort of alluded to this, there probably a lot of this work's being published in dermatology journals, and an expert on melanoma or psoriasis may not necessarily be an expert in AI, and just kind of what your observation has been and maybe opportunities for improvement.
Yeah, so my observation has been that, there are several of us in this space, and so we get inundated with review requests, and it gets very hard. I will say, like, as maybe a small conflict of interest, I am an associate editor at JID, and I've been trying to sort of set up guidance around the important thinking about like things like data sharing, particularly. And so I think several things. I think the way that we can improve it is, one, some of those papers may need like if it's a melanoma paper, it might need a melanoma expert reviewer and a technical reviewer that's not a clinician. Obviously, it would be most ideal if you have someone who has background in both, because there are some things that you may catch. And so I think like one thing that I have been sort of saying to the journals is like, we need to have we need to have data sharing and code sharing. I can understand why data sharing is not always a possibility when you're dealing with clinical images that may not be fully de-identified or your institution doesn't allow it. But there are ways to essentially, which is what Model Derm does, and I give them a lot of praise for this. They released an API online. So they don't share their code because they are also trying to commercialize, but they have an API online so that people can actually test out how well their algorithm works. And so there should be still some like bare minimum standards. So if you're going to make claims, like I think the journal should require some kind of code or API to be shared, even if the data isn't shared. I will add, actually, Veronica Rottenberg would give me a hard time if I forgot to mention this, that the International Skin Imaging Collaboration AI Working Group, which I'm a part of, wrote a guidelines in JAMA Dermatology called the Clear Derm Guidelines, which we actually wrote with reviewers and editors in mind about what things need to be reported out and what considerations need to be had. And so I think one thing is like me and others in this group, others who do research in this space, trying to educate everybody so that, we have more interested people and a bigger reviewer pool, but also like trying to write things out to make life easier for editors and reviewers in this space about what they should be seeing reported out in these papers.
Thank you. And I think we should probably wrap up now. Thanks so much, everyone, for asking questions and attending. I think this talk is recorded, if I'm not mistaken, and we'll be sharing it on our YouTube very soon. So if you missed anything or wanted to go back to it, you can. Thank you again for joining us and teaching us all about AI.
Thank you so much for having me.
Pleasure. Bye, everyone.